Today we're talking about chapter 1.4, which is transformations of functions. And before we start looking at how functions can shift or stretch or reflect, I also need to talk about symmetry. So there are three types of symmetry that we study for AP Pre-Calculus. The first picture shown is y-axis symmetry. And if you take a look at the points that they have here, they have like negative xy and xy. So we could make up some numbers for that. Like if we have the point 2, 4, then the point negative 2, 4 also has to exist on this graph if it has y-axis symmetry. This is also known as an even function. And if we're looking at kind of what these two ordered pairs say, remember y is the same as f of x. So f of negative x should equal f of x, right? When I plug in negative x, I get the same f of x. This is f of negative x, this is f of x, and they're the same value. All right. The second graph is showing us what we call origin symmetry. And origin symmetry means that the function is called an odd function. Even and odd are related to, if these are polynomial, they're related to the exponents that you see on the terms. We'll talk about that in a minute. And for an odd function, you can see you have points in opposite quadrants. We have quadrants 1 and 3 here. The points could also be in quadrants 2 or 4 as long as they're diagonal from each other. And if you think about this, this is like if we had the points 2, 3, then the point negative 2, negative 3 has to exist, the exact opposite sign of both the x and the y coordinate. So that means when you plug in negative x into whatever this function is, let's say it's x cubed, or well, let's say it's cube root of x or something. If you plug in negative x, you get the exact opposite of what you get if you plug in f of x. So if I plug in f of 2, I get 3. If I plug in f of negative 2, I get the exact opposite of 3. I get negative 3. And finally, this is called x-axis symmetry. We classify the first two as even or odd. This is not a function. Unofficially because of vertical line test, officially because some inputs have more than one output. And I'm just going to make a note of that. Each input has a plus or minus output for this scenario. Okay, so we don't have rules for function notation like what happens if you plug in negative x because this is not a function. All right, so let's take a look at some equations rather than graphs. Graphs are easy to just look at symmetry and decide. But if you just have equations, we're going to use this function idea here to see what's happening. So when we use a function, we're going to just be testing for even or odd. Neither does not mean, not necessarily, I don't know if I spelled that right, does not mean x-axis symmetry. For x-axis symmetry, you would be looking for like, do I get a plus or minus y? But we're not going to look for that. We're just looking for, is it even, is it odd, or neither of those two? All right, so what we should be doing is plugging in negative x. And if we get the exact same equation, when we plug in negative x and simplify, we have an even function. If we get the exact opposite, meaning all signs change on every term, then we have an odd function. So let's check it out. F of negative x would be plugging in negative x and for all of these x's here, and then simplifying and doing the math. So when you cube negative x, you get negative x cubed, but then the negative that's out in front is going to become positive x cubed. This will be minus 2x, and this will be minus 5. So is this the exact same thing that we started with? No, so not even. This is f of negative x, by the way. Is this the exact opposite? The exact opposite would be, let's take a look. If we go back to the original and distribute a negative through, it would be x cubed minus 2x plus 5. So no, we don't have the exact opposite. So this is actually neither. Let's just take a look at this first one. I'm not going to graph every single one of these, but just to kind of see what's going on. What do we mean by neither in this case? So what does this graph look like? Yeah, so this is not symmetric across the y-axis. It doesn't have origin symmetry. It might have its own little axis of symmetry somewhere, like right there. But that's not one of the two classifications that we're looking at. So that's what we mean by neither. All right, number 2, same thing. Let's plug in g of negative x. When you plug negative x and raise it to an even power, you're going to get the exact same thing that you started with. This is exactly g of negative x is exactly g of x. That's the exact same thing. So by definition, this is an even function. And our third one, h of negative x, this is going to be negative 2x. And then when we plug negative into x to the fifth, we'll get a negative out. So this will become plus x to the fifth. This is the exact opposite of the original h of x, right? This is just h of x with a negative distributed through. So this is an odd function. Okay, so what do we notice about even and odd? For even, we had all even exponents and a constant, and that constant didn't mess anything up because we were looking for signs not to change. For odd, we had all odd exponents. This was to the first, and no constant to mess things up. And then in number 1, we had all odd exponents, but the constant was sort of the problem. Shifting a graph that would have origin symmetry up or down is going to take it away from its origin symmetry, and then it will also not be even. Write another ordered pair that must exist on f of x, given that 3, negative 1 is on f of x. So we know that to be true. And the function has the following symmetry. So the function is odd. Remember, an odd function means that f of negative x should equal negative f of x. So therefore, if 3, negative 1 is on f of x, then also f of negative 3 has to equal the opposite of negative 1. So negative 3, positive 1 has to be on that graph. If that's confusing, then just give yourself a sketch. Plot the point 3, negative 1, say it's here. So for origin symmetry, I have to be over here in quadrant 2. So what would that be? If I'm over 3 and down 1, I'd have to be 1, 2, 3, left 3 and up 1. What about this x-axis symmetry? We just kind of ignored it in the previous section. So let's sketch the graph again. 1, 2, 3. Here's 3, negative 1. We need to have x-axis symmetry. So we should have another point at 3, positive 1. So maybe a picture was a better way to go about this anyway. F is even. Plot the original point, 3, negative 1. Even means y-axis symmetry, so it's supposed to be over here. So that would be negative 3, negative 1. And again, that's because if we had, instead of numbers, if we had A's and B's and things, again, this is because f of negative 3 has to equal f of 3 exactly. F of negative x has to equal f of x. Okay, what about transformations? Now, all of our parent functions that we're going to be working with, shifting, reflecting, stretching, I'm just expecting you to have worked with these in Algebra 1, a little bit in geometry, a lot in Algebra 2. And so I would expect you to graph the nice points, meaning the integer points, that would fit in a 10 by 10 grid. So I am not going to be asking you, I'm not going to be requiring you to change your scale if you're graphing any of these by hand. But we just want the points that are nice. So if we have a linear function, how many points do you have to plot? 2 points. 3 points would be fine, but 2 is the minimum. What if we have an absolute value graph? How many points do we have to plot on an absolute value graph? About 3 points. One of the points should be the vertex, and then 1 point on either side. Both of these graphs rely on slope, and because the slope is not changing from one side to the other, you're not going to need a bunch of points to get the correct shape. Okay, what about the square root of x graph? Think about all of the nice points that are on the square root of x. So 0, 0, square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. So these are the 4 points that I would expect you to graph on a square root graph. If we start stretching and shifting and some of these points are off of our 10 by 10 grid, then you don't have to plot them. Parabolas for an x squared graph, the original points are 0, 0, that's the vertex. Both plus and minus 1 will square to give you 1. Plus and minus 2 will square to give you 4. Plus or minus 3 will square to give you 9. So I've got that series of points that I would expect to have on a graph as long as it fits. The cubic function, almost wrote cubic, x to the third. So we should have 0, 0, which is the center. And then there are negatives and positives. So let's do the negatives first. Negative 1 cubed is negative 1. Negative 2 cubed is negative 8. Also 1 cubed is 1. 2 cubed is 8. And finally, for our rational function, where we have y equals 1 over x. So that does not have 0, 0. That has a vertical asymptote. We'll talk more about this in chapter 2, but for now, vertical asymptote at 0, horizontal asymptote at y equals 0. So it's got this little dotted line where no points are plotted. And we talked about why. Because of domain and range, x can't equal 0, y will never equal 0. And then what are the nice points? There's really only 2 nice points that I'm expecting you to plot and then work with as far as stretching goes. We've got 1, 1, and negative 1, negative 1, right? 1 over 1 is 1. 1 over negative 1 is negative 1. Okay, so knowing that we need all of those points, I just want to remind you of your transformation rules. Again, these should not be brand new, but if they are, or if some of them look unfamiliar and you need to practice them more, just come see me. These are easy problems to make up in practice. So first of all, vertical and horizontal shifts, these are the ones that make sense. Vertical anyway. Makes sense. Plus means up, minus means down, right? That's if you're adding or subtracting something on the end of the function. Horizontal shifts are kind of backwards. I'm going to say seem backwards. We can get into why this is the case later, but if you have subtraction inside of a function, then you're shifting to the right. And if you have plus c inside of a function, that's actually shifting to the left. So in my brain, that's kind of opposite of what I would think. And again, we can think about why a little bit more after these notes. What about reflections and then dilations, which are stretches and shrinks? They're actually the same rules. Reflections are really just a special case of dilations, but we'll look at them separately for now. So reflections are when you're flipping the graph over the x-axis or the y-axis. So x-axis is when you have a negative out in front. That means that every xy that you had on the graph is now going to become x opposite of y. So if y was already negative, then y becomes positive or vice versa. And then a y-axis reflection is if you have a negative on the inside of the function, every xy will become negative xy. And then the rules are similar for dilations and shrinks. So let's take a look at this. I've got some AP wording for you. I used to always just say stretching and shrinking horizontally or vertically, and it's still good to know what that is, but I'll show you some of our AP questions. We need to know what the dilation factor is. So C is a real number. A dilation in the graph, a dilation means a stretch or a shrink. So we use dilation for everything. Here are the rules. If you're going to have a vertical stretch or a vertical shrink or a vertical dilation by a factor of C, then you have the C value that's being multiplied out in front of your f of x. So if C is a number greater than 1, so if this is like 2 times f of x, then you get a vertical stretch because every x value stays the same and every y value gets multiplied by C. And it's the same thing for if C is a fraction. But think about this. If you're multiplying by 2, you're stretching out the y values. And if you're multiplying by like 1/2, for example, then you're cutting the y values in half. So vertical dilations are just by a factor of whatever C is exactly. Now, horizontal dilations, of course, are backwards again. So these are the ones that don't make as much sense when you're looking at them. A horizontal shrink is if you have some number multiplied on the x, which is like inside of the function, and that number is bigger than 1. I put absolute value here because if it's negative, this rule still applies, but it would be like a reflection and a dilation. Okay, so what are we doing here? We're taking every x value and dividing by c, and then y would stay whatever it normally is. So the reason we say this is a dilation by a factor of 1 over c is because if we see a 2 right here, we're going to divide every x value by 2, and so that's a shrink. Everything's going to get skinnier. If we have a horizontal stretch, it's because the c value that's on the x is a fraction, like maybe it's 1/2 times x. So we're still saying x divided by c, x divided by 1/2, which is y. Our AP problems are going to be like multiple choice, probably, and we'll have to look through like what is the correct dilation factor. They might not say shrink or stretch. They might just say horizontal dilation, and we have to pick out the correct factor. So let's talk about this. Describe the sequence of transformations from F to G. All right, so we do, I'm going to call them dilations. Dilations and reflections get listed first, and then any sort of shifting, vertical or horizontal, is last. Okay, so we have a vertical dilation by a factor of 2, right? Whatever C is, that's the exact factor. It's going to be a stretch. And then after that, this is a shift right 4 up 3. So shift right 4 up 3. Doesn't matter what order you could set up 3 and right 4 for that. Okay, for this one, we have a negative on the outside. That's an x-axis reflection. This 5 is on the inside. Remember, our dilation factor is 1 over c. So I'm just going to say horizontal dilation by a factor of 1/5. This should be a horizontal shrink, so the graph is 1/5 as wide as it was originally. Okay, and then the minus 12 is down 12. The reflection and the dilation, those two steps are interchangeable. They can be first and second, whatever, and then the down is afterwards. Okay, now we have a special case on number 3, so put a star next to this one. If we see a horizontal dilation and a horizontal shift, we have to unsimplify this thing. Factor the 2 out. Now, when I say factor it out, it's still inside of the big parentheses. It's just not distributed through. And so this shows me that I have a horizontal dilation by a factor of 1 over 2. And instead of saying shift left 6, it's not left 6. It's actually shifted left 3 units. All right, so we have to be careful of that. Here's an example of an AP question. The function f is given by 3x squared plus 2x plus 1. The graph of which of the following functions is the image of the graph of f after a vertical dilation of the graph by a factor of 2? What does that mean? The factor for vertical dilation is every y value got multiplied by 2, right? And every x value stayed the same. So all that means is we should be looking for the function that's 2 times f of x. So I'm just looking for the one that has a 2 distributed through. I don't see any others that have that same equation, so it has to be this. It says this is the multiplicative transformation that results from multiplying f of x by 2. So different phrasing for that as far as the reasoning, but yeah, that is our vertical dilation rule. Okay, what about sketching graphs? So plot all the nice points that fit on a 10 by 10 grid. These we don't have to write out formally for AP. We just want to get these graphs. So first you need to note the parent function. And I always do, again, dilation and reflecting first, then shift. If you do it out of order, you're going to get the wrong graph. Okay, so the original points that we have on the x squared graph, I'm going to write those out. And then after that, I'm going to say this negative 2 out here gets multiplied by every y value, right? That's a reflection and a vertical dilation. So the original points are 0, 0, plus or minus 1, 1, plus or minus 2, 4, plus or minus 3, 9. You don't have to write these out, but I think it's just good for my brain to keep track of that. So do the math on this. Multiply every y value by negative 2, but leave the x values the same. And when I get to my last set of points, I'm not going to plot plus or minus 3, negative 18. That's going to be too big. Now, don't plot these points yet, because remember, we have to then take them all and go right 3, up 4. So you can, again, write out the math for that. Usually I just do this. I hover my pencil over 0, 0, and then I'm going to say right 3, up 4. Now, you can do that for every point, or if you have a negative 2x squared graph, like you can kind of sketch the shape out of this, right? Like I know that normally the next point for negative x squared is over 1, down 1. If it's negative 2, it's going to be over 1, down 2 on either side. And the next one would normally be over 2, down 4, but it's going to be over 2, down 8. Now, if that's confusing, if you're like, what are you doing? Just go back here. Negative 1, negative 2 was one of the points, and then I'm supposed to go right 3, up 4, and that lands me on my first point. And then positive 1, negative 2 was a point, and then go right 3, up 4, that lands you there. My next points are going to be off the grid. So when I sketch this in, I know it's supposed to look like a curved parabola, so I'm doing my best here. You don't have to extend it all the way past the graph because you don't want to get inaccurate with your arrows. Okay, what about the square root graph? So the original points on the square root of x graph are 0, 0, 1, 1, 4, 2, 9, 3. Well, what are we going to be doing to this? So we have a number on the x. Every x value is going to get divided by 2. Horizontal dilation, factor of 1/2. Every y value is going to get multiplied by 3. So these are my favorite that we don't have to shift around because we just do the math and then plot the points. So the key is just doing the math correctly. If a number doesn't divide by 2, we're still going to plot it. Or if it doesn't divide nicely by 2, we should still plot it. Don't skip over that. So nothing to shift. This is just 0, 0, 1/2, 3, 2, 6, and 4.5 up to 9. Remember, I always give you 10 by 10 grids so you can kind of save yourself some sketching here. Now, what happened to this graph? It's been vertically stretched because of the 3, and it's undergone a horizontal shrink because all of those points are closer together than they were. Absolute value graphs should be the easiest points to plot for us. This negative 2/5 should tell you that the absolute value opens down, and then the slope on either side is plus or minus 2/5. So use that as a slope, whether it's inside of the absolute value or not. And then the vertex should be left 4 and up 3 from where it was. So negative 4, 3 is where the vertex is. And then to get this graph, I'm just going to go down to right 5 on one side and down to left 5 on the other side. And if you go back a page or two, we said, you only need 2 points on an absolute value graph. That's good enough. If you're going to extend your arrows much further out, you need to keep plotting that slope. Don't just sketch it out all the way. Okay, and then what about this rational graph? So remember, the original graph is just 1 over x. That's what we're comparing it to. So this has just been moved left 3, down 5. Remember, these shifts affect our horizontal and vertical asymptotes. So there normally was a vertical asymptote at 0, but now it's going to be at negative 3. And there was a horizontal asymptote at 0, but now it's going to be down 5. And remember, the original points are like 1, 1, and negative 1, 1. So if you go left 3 and down 5, there's 1 point. The other point fits in the other corner. And you just sketch these branches to be smooth curves. Don't go too far out with them. They should not cross through either of the two asymptotes. We will do more complicated rational graphs in Chapter 2, but for now we're just transforming this parent function. Okay, here's another AP problem. F and G are defined for all real numbers such that g of x equals f of 2 times x minus 4. So they've got this unsimplified for you to show you that we're shifting to the right 4, and this 2 is a horizontal dilation. Remember, the factor is not 2. Every x value gets divided by 2. So it's a dilation of 1 over 2. Which of the following sequences transformation maps the graph of f to the graph of g? Okay, so let's look at our options. Horizontal dilation by a factor of not 2, not 2, 1/2, yes. And then they didn't say right 4, so let's look at this. 8's out. Followed by a horizontal translation of the graph by negative 4 units. Which one of these is correct? Negative 4 or positive 4? So normally we don't do the math, right? We would just say, okay, if there was a point at 0, 0, just make up a point. If there is a point at 0, 0, after you've done the horizontal dilation, you're going to move this to the right 4 units. So that's going to be, I just moved it up. After you do your horizontal dilation, which will still be 0, 0, if you're going to the right 4 units, it's going to be at 4, 0. Maybe what I should have done is plot some points, right? So what are you doing to the x values? You're adding 4. So this should be D. Okay, I'm not sure how we're doing on time. These are our last 2 problems. What if we don't have a parent function? What if we just have some weird f of x? So same rules apply. I see that I have a horizontal something happening, a reflection, and a horizontal shift. So we've got to factor that out first. So what's happening? Every x value gets divided by negative 1. Every y value gets multiplied by 1/2. And then after that, we're going to shift to the right 3. You're given a graph. The original points are negative 1, negative 2, 0, 0, and 7, negative 2. So let's do the math here. This becomes 1, negative 1, 0, 0, negative 7, negative 1, and then all those points go right 3. So 1, negative 1, and then go 1, 2, 3 to the right. 0, 0, 3 to the right, -7, -1, and then 1, 2, 3 to the right. Connect these points with little linear segments. And remember, this should look like a y-axis reflection, so the arrow that was going to the right should now be going to the left. All right, next one. Every y value gets multiplied by -1. Every x value gets divided by 1/2. So that's a horizontal dilation by a factor of, instead of dividing by 1/2, it's a factor of 1 over 1/2. It's a factor of 2. So this is a horizontal stretch. The original points are -4, 2. 0, 0 is supposed to be on there. 4, 9. And 8, 4. After that, we're going up 4 after we do all the dilation stuff. So multiply everything by 2. -8, -2, 0, 0, 8, -9. And this one's going to be off the graph, 16, -4. We should still think about where that is. We might sketch it in just so we get the right shape. And then we're going up 4 after that. Okay, so -8, -2, but then go up 1, 2, 3, 4. 0, 0, up 4. 8, -9, and then up 4. And 16, -4, let's just say that's like way out here. Oh, wait a second. Sorry. This point is one off. I was supposed to go 8, -9, and then 1, 2, 3, 4. I had that at 9. And then, like I said, 16, -4 is somewhere out here. We'll just make a note that it should be like at 0 again. And then all of these points get connected by little linear segments. That's why I wanted to have one more point on there so you could still get the full shape of the graph. Okay, that's it for today. That was kind of a lot to throw at you. Try the homework tonight and come into office hours if you have questions.